Our presenters today are Mark Dowd and David Dewey, X-Force research engineers, and Ryan Smith with iDefense Research.
Hi, my name's Mark Dowd. This is David and Ryan. Like you said, we're at ISS and iDefense. We actually changed the name of our talk to Attacking Interoperability, but it's the same talk. So before we got started, we just wanted to quickly talk about what exactly we meant by interoperability in the context of our speech. So basically, for the material that we're going to be presenting today, interoperability refers to basically the software that's responsible for translating data between two different cooperating components within a bigger application. So it's kind of like the analog of a language translator. Obviously, they can't communicate directly. They need a path of communication who can interpret from each side to make communication possible. To give you an idea about some of the interoperability layers that are present in contemporary web browsers, we've drawn a bit of a diagram here, and it basically depicts some of the elements and kind of things that we'll be talking about later. So, you know, every component that interacts with each other directly requires a new interoperability layer to be added. So you can see there in the diagram, all the arrows represent basically interoperability layers that had to be built in. So you can see we've got like the DOM and JavaScript and VB script and a couple of other like plugins in Java and so forth that all need to have layers of interpretation between them. So basically our thesis was that this interoperability created a new and large attack surface that has previously been largely unexplored. You know, a lot of people have been focusing on things like attacking ActiveX components or the browser itself or something like that, but there's been very little attention to date being paid to the marshalling layers responsible for communicating the data across those boundaries. So we actually are targeting contemporary web browsers for this speech, but a lot of the concepts that we want to present here have implications beyond the browser to any software that does similar sort of interoperability. So we've divided the speech into roughly two sections. We've got the attack surface, and it's kind of like a whirlwind overview of some of the technologies that you need to be familiar with to understand the later content. But we've actually released a paper today, and I'll give the URL later, that goes into a lot more depth, and it's a lot more comprehensive about each of the technologies that we're going to briefly touch on today. Then we're going to talk about the vulnerability classes that we came up with and the results. The result that we're hoping to present here today is that we uncovered subtle vulnerability classes that are relevant to all contemporary web browsers, and a lot of the associated vendors that do like plugins and stuff like that are going to need to be aware of as well.
So as Mark mentioned earlier, we're going to talk a little bit about the attack surface first. So with interoperability, there's actually a very large attack surface. So there's scriptable plugins, communication and marshalling, language and DOM runtimes, and all of these things need to talk together. So if you look at the diagram to the right, that was to the right, we've actually have a graph of interoperability. With interoperability, the attack surface is large, and as the attack surface grows, so does the bling. The unique interoperability also has unique bug classes, and as unique bug classes increase, so does the bling. So the way we figure it, with interoperability, with a large attack surface and unique bug classes, it's sort of more of an exponential curve, and we figure interoperability is about right there. So some of the unique bug classes that we're going to be talking about are object retention, type confusion, and transitive trust. So I'll learn how to do this one day. So scriptable plugins have been targeted a lot in the past. Lots of people have found vulnerabilities inside them, and there's plenty of ActiveX fuzzers. There's a lot of well-known bug classes such as integer overflows and stack overflows that have been hunted to death, but we're not really going to speak about that much in this speech because they're a little bit boring. The thing that we are going to speak about in this presentation is type manipulation and the lifespan of parameters, which is a little bit more interesting. So interoperability and communications, there's a really large attack surface, and it's incredibly difficult to program these things. They're charged with converting data from one representation to another, especially when two components that have disparate native representations of types that need to communicate with a similar type. They also deal with complex objects and have to do marshalling and serialization, which is also very hard. With the DOM and language runtimes, there's also a lot of native code that can be targeted, and they have to deal with the same sort of lifespan issues. So to the right, we have a map of the modern web browser, and each of those arrows actually represents a different interoperability channel that could potentially have vulnerabilities. So with Internet Explorer, we're going to go a little bit over ActiveX. We're going to talk about how plugins are registered, and we're going to deal with some component object model stuff and data manipulation. And so there's also the NPAPI, and Firefox, Safari, Chrome, Opera all use that API. We'll talk a little bit about the plugin registration, their version of the COM stuff, which is NPAPI and the NP runtime, and their version of variants, which is NP objects and NP classes.
All right, so as was mentioned, we're going to talk a little bit about the background technology that everyone's going to need to have a basic understanding of in order for the rest of the talk to make any sense whatsoever. So first we're going to talk a little bit about ActiveX. Everyone in this room should probably understand what an ActiveX control is, but just as a quick overview, ActiveX controls as they're installed on your system are registered in the registry under the HK classes root. They're cataloged in there by class ID, so that if, for example, a web browser tries to load the ActiveX control, it will look up the class ID in the registry and be able to associate the actual library with the ActiveX control it's trying to be loaded. There's been a few functional restrictions that have been applied to Internet Explorer to try to control the instantiation of ActiveX controls. One of these is the safer initialization setting, also in the registry on a per class ID basis. This basically determines whether or not an ActiveX control can be resurrected from a persistent stream, which we'll talk about in more detail later. Safer scripting determines whether or not the control can interact with any of the scripting languages or scripting engines that may exist within Internet Explorer. A few more restrictions that have been added. Site lock allows a developer to determine which domain a control can be loaded from at compile time. There's system-wide kill bits. The kill bit is a feature that allows you to restrict the instantiation of a particular control based on class ID. In IE8, the ability to restrict kill bits on a per user basis was added. There's a few other types of restrictions where, like in IE7, there's a system-wide whitelist of controls, so you can start with a whitelist of controls that are allowed to be loaded and then optionally add controls to that list as time goes on. And then in IE8, that's added at the per user and per domain level as well. So ActiveX controls, once they're loaded within a web browser, are scriptable through the iDispatch and iDispatch EX interfaces. These interfaces are self-publishing, so the COM object itself will tell the browser which object properties and methods are available and can be interacted with through JavaScript. Those methods and properties are accessed using the invoke method in the iDispatch interface. Basically, you would pass, as an argument to invoke, you would pass the name of a method that you would like to execute, and you pass the arguments to that method in a disparams structure. A disparam structure is essentially just an array of variant args. We're going to talk a little bit more about the variant structure here in just a bit. But basically, what I've just described is if you were trying to interact with an ActiveX control through JavaScript and you call a method, that method name is passed into the invoke method in the iDispatch interface. So the variant data structure is one of the key data structures that's used in the marshalling of data between the Internet Explorer and any of the plugins that it supports. Basically, it's just a data structure that defines the type of data that's going to be contained within the structure. Depending on that type, sometimes there's some metadata in there that will describe things like size. So like a beaster will tell you how long it is, and then you just have the value of the data itself. The different data types that are supported, they range from 0 to 0xFFF. As you can see in the table below, there's some very common data types that you're used to dealing with, if you were coding in C or something like that, where you have integers and character strings and those types of things. But additionally, there's going to be some very complex data types that are supported in invariants, where you can basically represent entire other objects within the variant itself. So you can have effectively a variable that represents a whole other object. There are some modifiers that can be applied to the variant type that's carried in the variant data structure. These are just bit masked onto the variant type that can change the way that data is actually represented and should be interpreted. So for example, you see down here in the modifiers, for example, there is a byref mask that can be applied, and what that would mean is that instead of having an integer, you could have for example, you could have a pointer to an integer. So you can kind of see where this is going, where when you read a pointer to an integer is an integer, right? And you could see where some of the mistakes that we're going to talk about in more depth might come from with the misinterpretation of those types of data. It's important to understand that these modifiers are not necessarily mutually exclusive, so you can have a pointer to an array, for example. A VT array would create a safe array of variants, so in that case you'd have a pointer to an array, and then by masking on the byref modifier, you can have a pointer to an array. So COM serialization and COM persistence is basically the ability of a COM object to store its object state between instantiations. Basically, in the terms of ActiveX, this would allow you to save the state of an ActiveX control and then reload that state as the browser is reloaded. These are accessed through the COM object through the iStream and iStorage interfaces in the COM object. Basically, it's a binary flat file that represents the state of the object at the time that it was saved. This allows you to resurrect that object. The object would read the persistent storage through the iPersist interface and basically try to resurrect the state of the object from what's read out of that file. As I mentioned, the persistent stream is just a binary data representing the object properties. This is applied to the COM object through the iPersist load method. As you can imagine, there is an infinite number of ways that a developer may choose to store the state of an object and what elements of an object they may determine is important or not important. So to try to create some standardization around how objects are stored and loaded, Microsoft added the iPersist stream load method in the ATL. Most COM objects that you'll come across on a Windows operating system use this method to load the data from a persistent storage. When a developer chooses to use the iPersist stream load, what they do to be able to define the format of the data that's going to exist there, they create a property map. And that property map is a way in code where they can define what the format of that binary file is going to look like. Because obviously if you're going to be storing multiple different variant types at different offsets throughout the binary format, the COM object itself has to know where to read what and understand what it's reading as it reads that binary stream. So there's a number of ways that you can load object persistence into ActiveX Control and Internet Explorer. One is through the use of the param tags. The param tags that are associated with an ActiveX control will interface with the iProperty bag interface and allow you to set property values of the object at instantiation. The one we're going to focus more of our attention on is the persistent stream instantiation, which is done through an object tag. The data parameter of an object tag allows you to specify a URL to this binary file that would then be interpreted by the, in many cases, the iPersist stream load method. So here is a just kind of a contrived example of what this would look like in code. As you can see here above, this COM object implements the iPersist stream init interface. In the property map, you can see that it defines a series of data types that would be stored in the persistent stream. They're just, integer and integer and a couple of strings. And then as you look down at the binary format, this is what the binary file would have to look like in order to match this property map and then be loaded into the COM object through the data parameter in the object tag.
Okay, I'm just going to go over the NPAPI runtime and the NP runtime, sorry. So with the NPAPI, plugins are registered in one of two ways. Basically, you can copy the plugin into the browser's respective plugin directory, or you can add a key to the registry. It sort of depends on which browser and all that kind of stuff, but essentially, we document that more thoroughly in our paper. So registered plugins with the NPAPI are typically associated with content types, and they do that by associating it with either one or more MIME types, or you can associate it with one or more file extensions. This information is contained within the version information within the DLL of the plugin object. So the NPAPI is divided into two parts basically. You have the browser-side functions and the plugin-side functions. So the browser-side functions are basically the API that the browser exposes to the plugin, and it basically offers a bunch of services to the plugin. It's passed to the plugin during initialization in the form of an NP Netscape funcs structure, and typically the naming convention is for those functions to start with npn underscore. So basically, this has a whole bunch of functions that the plugin can use to request services from the browser. Alternatively, there's the plugin-side functions, which is basically the implementation of the plugin that gets passed to the browser during initialization, and this defines, all the functionality for the plugin itself. So these are passed to the browser at initialization in an NP plugin func structure, and by convention, their naming usually starts with npp underscore. Now, if you want to make your plugin scriptable in JavaScript, and by that I mean you can get it from the DOM and access properties and methods from the plugin, then you have to expose a scriptable object to the browser. And the way you do that is by one of the plugin side functions, npp getValue. This function can actually be queried by the browser for a whole bunch of different properties of the plugin, but one of them in particular is the nppv plugin scriptable NP object. And basically that's, if you try and script a plugin object, the browser will query for this particular property, and then if it's present, then you can script the plugin. Now, when the browser queries for this object, what it actually gets returned is a structure called an NP object. And an NP object is basically just a reference count and an NP class structure, which is pictured there below. And it basically defines all the behavior of the object itself. So the NP class structure, it has a number of functions that can be used to basically simulate setting properties, getting properties, and invoking functions from JavaScript. It basically has three methods for getting and setting properties, which is the has property, get property, and set property methods. And then for invoking as well, it also has method and invoke. So the diagram here basically shows the process that occurs when some JavaScript code tries to access a property on the plugin. One thing we should note is that when variables are passed from JavaScript to a plugin, they're passed as NP variants, and these are basically the analog of the variant structure in the Microsoft world. Again, it's a simple type and value structure. The value is a union, but it's a lot more simplistic than the Microsoft equivalent because there's no composite types. You just have basically an enumeration of a small amount of types there, and they define what's in the union. Now, so when the plugin gets variables from JavaScript, it basically manipulates them using a number of macros defined in the NP runtime. There's three types of macros. One of them is NP variant to XXX, and XXX is the type, so it might be NP variant to int32, NP variant to string, etc. There's the reverse, where they're wanting to convert values that will travel back to JavaScript, and then there's the NP variant is XXX, which basically checks the type of the union. So basically, the marshalling layer actually creates a proxy object in both directions when you try and pass values from JavaScript to the plugin and vice versa. Essentially, it'll create an empty JavaScript object, and when you try and call a method on it, it will reroute the call over to the NP runtime, which will communicate with your plugin. That's not particularly relevant, but Ryan did a really cool diagram, and I basically wanted to put it in. All right, so we're gonna, that was a really brief overview, and like I said, our paper goes into a lot more depth about all that sort of stuff, but we wanted to start talking about some of the vulnerability classes and results that we've found when looking at this stuff. So, of course, the interoperability code that we looked at is affected by standard bug classes. You've got buffer overflows, memory corruption, all that kind of stuff, but we don't really want to talk about that because it's already like well-known stuff. What we found is that there's complexities that are unique to interoperability layers. They have to handle the sharing of data, they have to have language agnostic variable representation, and they also have to take into account that the security models of different plugins might be divergent. So in our research, we basically found what we think is unique classes of vulnerabilities. Now, for each of these, in the past, there's been one or two examples of each that you could go back and find, but they were kind of considered esoteric or one-off. What we found is a number of code constructs that, for each of these vulnerability classes, that are easy to make by the programmer, and they're repeatable, and they have pretty severe consequences from a security standpoint. So we're basically going to talk about object retention vulnerabilities, which is to do with the management of the lifespan of an object. We're going to talk about type confusion vulnerabilities, which is basically mistaking one data type for another. And we're going to talk about larger trust issues, which is basically, like I said at the introduction, when two objects communicate directly with each other, they implicitly extend some level of trust to each other.
So the first vulnerability class we're going to talk about is object retention. So basically with object retention, you have these data structures that are being shared between multiple components. And in order to do this correctly, they need to have something where they know when to release it back to the operating system, but not do that too early. And at the same time, they need to know how long they need to keep the object for. So the strategy that's normally employed in the material that we've reviewed as a case study is reference counting. And the idea behind this is the objects contain a reference count and increment it as people need to keep a reference to the object, and decrement it as that object is no longer needed. And we found that mismanagement of these is bad news for developers and good news for us. So really there's two types of lifespan mismanagement. There's releasing it too early, and there's not releasing it at all. And both of these things can lead to problems. When the memory is deallocated too early, then generally there can be pointers that are stale. It can lead to double freeze and other types of memory corruption. And when it's maintained indefinitely, not only can there be memory leaks, which might help when you're writing an exploit, but also these can potentially result in the memory being deallocated too early and the same sort of stale pointer problem. We're going to talk a little bit about how the APIs differ between ActiveX and NPAPI for object retention as well. So with the reference count, I've got big feet. So with the reference, no comment. So with the reference count, internally it's stored as a 32-bit integer on a 32-bit system. And the idea behind too many references also leading to exploitable conditions is that if you exceed the 4 billion mark on a 32-bit system, it can lead to one reference, and then if that reference is freed, it will cause the same stale pointers as if it had been released too early. So it effectively results in the same consequence. These are slightly more difficult to exploit. The problem is the browser can freeze if you try to increment it that many times. But the takeaway is that miscounting here is beneficial to an attacker. So with the NPAPI, there's two functions that are used in order to maintain these reference counts. There's retain object and release object, which do kind of what they say. When an object is actually retained without npn retain object being called, then the object can be freed and it will lead to the same sort of stale memory pointers. And also, mem copying NP variants can be potentially dangerous because if they store a pointer and later on you have two copies of NP variants and one of them is freed, that can lead to problems as well. But in practice, this is actually pretty rare. Also, when the get property function is called, NP retain needs to be called, otherwise it will lead to the same sort of problems. So in this example, the problem here that's highlighted is the object is retained, but there's no added reference. And this is bad because what will happen is it could get freed too early and the memory pointer will be stale. Also, failure to release objects is bad, leading to memory leaks like we had said before, and possible stale pointer issues. This example here is very similar to the last one, where npn, except now npn retain object is called. But the problem here is there's no release that will release the object after it's been retained, so it'll lead to the same sort of thing where the 32-bit boundary can be exceeded and the object will end up being released.
All right, so I'm going to talk a little bit about some of the object retention vulnerability classes that exist within ActiveX. COM objects manage their retention through the IUnknown interface, which exposes two methods, one called the addref method and one called release. These two methods, as Ryan mentioned, sort of do exactly what they sound like. Addref would increment the reference counter and release will decrement it. If you are, if you write code that receives a COM object, you need to make sure that the addref is called as the COM object is instantiated in order to avoid, the equivalent problems that Ryan just mentioned that exist in NPAPI. If you intend to retain the object, you must call addref, and when you're finished with it, you need to call release. So here's an example of a case where release is never called when the object is no longer needed. This could eventually result in the integer overflow issue that we talked about there at the beginning. Switching gears a little bit, in the world of ActiveX, variants also need to be handled with care. Variants containing pointers need to be handled extremely carefully. The issue is that you can get yourself into a scenario where if you're trying to copy a variant from one place to another, you may just be copying a pointer to a variant from one place to another, and if the original variant is freed, your copy is obviously stale. There's two different types of copying that can occur within the world of a variant. But basically, pointer values should not be copied. The target object should be duplicated. I want to make sure that makes sense. Instead of just copying the object, you need to absolutely duplicate the object and store a new copy of that object. In a COM interface, you need to make sure that the addref method is called on the new copy of the object to make sure that that object is that you're claiming, staking your claim to that instance of the object. Variant copy and variant copy IND handle duplication correctly. It's worth noting here that using these variant copies don't necessarily get you out of the woods. We're going to talk about some problems with those here in just a bit. Basically, how would a developer end up with a shallow copy? Oftentimes, you'll see developers use memcopy instead of one of the variant API functions, which results in one of these copies of an object as opposed to the duplication of an object. Here's an example where an object was memcopied as opposed to using one of the variant APIs. There was a bug exactly like this that was released in the last Super Tuesday in the Office Web Components ActiveX control. This was exactly what the issue was. There was a copy of the object made, the original object was freed, later references to the copy of the object obviously were stale.
Okay, so one interesting thing to note is that So you just assume, okay, I'll just use variant copy instead and that's safe. And that's possibly true, but not necessarily. So in the Microsoft variant APIs, they actually distinguish between two different structures, the variant structure and the variant arg structure. And they say that the variant structure is basically, they say something along the lines of this is for retaining an absolute value, which basically means it doesn't have the VT byref modifier on it, as opposed to the variant arg structure, which can be indirect and it has the byref modifier on it, or can possibly have the byref modifier on it. And they give two different functions for manipulating the different structures. There's variant copy, which copies an absolute value. You know, if you've got a com object in the variant, it will retain a reference to it, etc. But it does not copy things that have VT byref set. If you use variant copy IND, which stands for indirect, it will actually follow a byref modifier if it's there, and it will make a copy of the destination object. Now, in reality, variant arg and variant are actually an identical structure, and they're used interchangeably everywhere. So you can actually, of course, you actually can have variant copies that have VT byref set. It's no problem whatsoever. So if you actually pass a variant to some function that tries to retain a copy of it by using variant copy, and the variant you pass has VT byref set, then you have potential problems there because basically this will equate to a mem copy, and the object that you're indirectly pointing to can be released, and that would probably be bad. Whether it's exploitable or not sort of depends on how they operate on the variant afterwards. It's dependent on whether they actually follow the indirection and operate on the object for you. So here's a simple example of that. Again, they take a variant and they just copy it into a global property in this example. But like I said, if you can specify VT byref, this is actually just going to do a mem copy, and there's going to be potential issues there.
So the next vulnerability class we're going to talk about is type confusion. And so as we said before, interoperability requires that language agnostic data representation. And these are generally contrived types. In COM, there's variant and variant arg, and with the NP runtime, there's NP variant. And since these contrived types require careful programming in order to properly deal with them, it's a pretty big opportunity for attackers. So with type confusion vulnerabilities, they occur when one data type is mistaken for another. And generally, we found that these happen with type wildcards and also with unions. So with type wildcards, these allow a wide range of types to be used for a specific variable and completely negate the casting requirements for a C compiler. The specific thing that we're talking about with type wildcards is a void star pointer. Because when the wrong types are used and a void star is used, the compiler will not emit a warning, and because of that, the programmer may either not notice or not care at all. And because of that, it requires more diligent use to use properly. And we believe the solution is to ban void star. Not really, though, Microsoft. So these wildcards are normally used to protect the programmer from shooting himself in the foot. Basically, with that first line of C code we have up there, if you try to compile it, the compiler will emit a warning saying that it cannot convert the parameter from an unsigned long to a char star. The first warning is actually from the Visual Studio compiler, and the second is from GCC. However, we show in the next line that memcopy, where it's copying a long array to a character array, completely allows it without any warnings. And these areas where the types aren't resolved by the compiler and there's no compiler protections can be exposed to attack, which could lead to memory corruption or information leaks. So one example of a wildcard bug is the vid control bug. As you can see that line right there, they accidentally have an ampersand, and that's sort of a typo, I think, but it's hard to tell only looking at the assembly. And basically what this allows you to do is the PV data variable is actually a pointer, and it passes the address of a pointer instead of the address of an array, and it will read into the pointer, which will completely corrupt the stack. And this vulnerability was a lot of fun to exploit.
So Ryan talked about the idea of type wildcards. I'm going to talk about the concept of a union. A union is a way in code to represent multiple different data types within the same memory space. It's useful for conserving memory and abstracting data, and there's no warnings at compile time when you access the incorrect data type. The compiler really has no concept of what your intent was. But the idea is that you can represent different data type by the same variable name. It's up to the programmer to keep track of the appropriate data type that's stored within that variable. Oftentimes there's high-level identifiers to keep track, but it's also very easy to get wrong. A lot of times the APIs that take a union as one of these elements as an argument, the API names or the variable names don't necessarily lend themselves to giving you a hint as to what it's supposed to be. So, as has been going on with the start of the talk, we'll just consider the two technologies separately, ActiveX and NPAPI. So within ActiveX, there's a type confusion vulnerability that exists within variants due to permissive property maps. I mentioned earlier that the property map is the way that a developer would define what data types are supposed to be passed in through the persistent stream. There are ways that you can create property maps that basically land you in the exact same scenario as a void star, like Ryan said. Basically, you don't properly define what the data type is that would exist at a certain offset in the data stream, and because of that, basically any data type could exist there, and it's up to the developer to try to handle it. Some of the property map macros require a specific variant type and can easily help you lock down the data types that would be stored at that entry within the binary stream, like prop entry type EX, or prop data entry. Other macros that you use to define the property map are more permissive, like prop entry or prop entry EX. One additional point is that the more restrictive macros that are listed in the second bullet point can become permissive if the data type that's passed to them is VT empty. As you can imagine, if you can't clearly define what the data type is that's supposed to be interpreted at a certain offset in the persistent stream, it's up to the developer to try to understand what that data type is supposed to be. Well, in the world of ActiveX, where these controls could be loaded by presumably any third party, and a persistent stream could be passed in from presumably any third party, there's no way that the developer of that ActiveX control could properly understand what data type an attacker may be providing if they're using a permissive property map like this. So the difference between prop data entry and prop entry, it allows you the ability to write memory allocated for a property directly into the class. Basically, if you pass, as I mentioned, if you pass VT empty in as the type, when you use these macros in your property map, you'll bypass all the type checking that will be performed. That type checking is typically performed within iDispatch, but you can think of VT empty as the equivalent of a void star, like Ryan talked about before. So when iDispatch goes to perform the validation, it really has nothing to compare it against and doesn't know if it's right or wrong. And once again, there's a superfluous diagram here, but Ryan is really good at these. So. The second type of type confusion that we're going to talk about is initialization errors. Basically, this occurs when you start operating on a variant that has not been fully initialized. This is tantamount to operating on an object when this is sort of the same thing as operating on an object where its constructor was never called. So you can think of variants and objects to be very similar. And an object requires a constructor. Variants require initialization. Right, so if you were to call variant clear on an uninitialized variant, you can lead yourself into potentially exploitable conditions. Basically, the issue is that for some of the more complex variant types that I talked about earlier, where you can store an object type, variant clear will attempt to call the release method to decrement the reference counter that we talked about at the very beginning of the talk. It will try to call that release method for that object. But if that object hasn't been properly initialized, that release pointer could very easily point off into nowhere. So it's very important to remember to call variant init on any variant that you then call variant clear on. You can sort of think of it as like malloc and free. They sort of come in pairs, right? But calling variant init does not necessarily get you a free pass. You can still land in some of the more complex vulnerability classes that we're going to talk about a little bit later in the talk. It's also important to understand some of the intricacies of more of the variant API functions. Oftentimes they will call variant clear as part of that method. So you think you're sort of in the clear by calling variant copy, for example, but variant copy will call variant clear on the destination operand prior to completing the copy. So if you're trying to copy into an uninitialized variant, you'll land yourself exactly in this problem to begin with. So here's another example. This is an example of an uninitialized variant bug. This code is taken sort of from the ATL. The code that is in the ATL does not demo well because of some C++ intricacies that would take us another 30 minutes to explain. So we sort of summed it up logically speaking, but logically speaking, this is what one of the functions in the ATL does, where if it fails to read the stream, it will call variant clear on a variant that has never been initialized. This bug, as I mentioned, is in the ATL and has been compiled into many ActiveX controls that ship by default with Windows, as well as many third-party ActiveX controls. Here's a contrived example of what a variant copy vulnerability would look like. This is a very similar code to what we saw before, where in this case it's going to try to copy to a destination variant which has not been initialized, resulting in the same exploitable condition. So time for a demo. So what we've got here is we've got a browser that I'm going to point at a malicious web page. The exploit is left intentionally incomplete so that I can demonstrate the issue of what's going to occur. What I'm going to do is I'm going to load an ActiveX control that was compiled against the vulnerable ATL. It's going to pass in a persistent stream which will cause the read to fail that we saw in the source code there. It will then try to call variant clear on the variant that was not initialized. So I'm going to click this link here. This will pop us up in our debugger here, and what you can see is that, well, you can't see it. I'll make it so you can see it. What you can see here is we're crashing on a call to ECX plus 8. ECX plus 8 is the release method that I mentioned earlier for that object. It's trying to decrement the reference pointer for the object because it thinks it no longer needs it. Unfortunately, this object is stored on the stack. It has not been properly initialized, so where you see where it's trying to call to 3A12001A, that's simply residual stack data that just lived on the stack at the time of the crash. So we got extremely lucky here because obviously this is a pretty easily exploitable condition. So I'm going to go ahead and do that for real. Successful exploit, hopefully. Let me do this real quick too, just so you know there's no shenanigans. They told me not to say shenanigans. I don't know why. You can see the current list of listening ports. So I'm going to go to the successful exploit, which, as you saw, we're calling into we're trying to call a fairly reliable address that had no memory mapped in it. So what we're going to do is we're going to use the technique that was presented by Mark and Alex Soderov last year, where we're going to place a .NET binary at that location containing our shellcode. So we click that guy. And if we come over here, you can see we're now listening on port 8721. And we've got a shell. The reason that I'm sorry, the question was why do we consider that a type confusion error and not a reference counting error? The issue is that the reference counting function is actually never called, right? It's not an issue where it was called and not properly, and not called where it should have been. It actually was attempted to be called. The reason it's a type confusion error is because let me do this while I'm talking. The application is assuming that it's going to be a variant type that it's not. And it's trying to call variant clear on a variant type that it should not ever try to call variant clear on, because it's assuming that it's something like an integer or a string, when in fact it was a VT class ID, which is an unsafe variant type to be calling that on.
Okay. Another type of mistake that's really easy to make, particularly with the ActiveX variants, is misinterpreting types. Basically, the problem is, like we outlined before, the variant type is not a simple enumeration. It is a basic object with potential modifiers, and those modifiers are also not mutually exclusive. So it's very simple to make mistakes when you're interpreting the type and erroneously access the data in the variant as a result. So this type of interpretation, there's basically a couple of different constructs that can go wrong. So one of them is masking off some or all of the modifiers, and this is basically where you just try and access the basic type, or you check whether the presence of one of the subtypes is there without verifying that the other one isn't there, and you often have easy mistakes to make. And just to give you an example of that, something might check if VT array is set, and if it is, they'll go ahead and use the safe array data structures. But just because VT array is set, it doesn't mean it's a safe array. If VT byref is also set, then it's a pointer to a safe array. So you'll have like some sort of memory corruption as a result. So I actually found a vulnerability just like this in the core of Internet Explorer, and this was in the interoperability layer for the DOM. So basically, all of the code that all of the functions that want to call access the DOM, access data through access the functions through these marshalling layers, and the marshalling layers basically all use some of the common code, and this code is an approximation of where the vulnerability lies. So you can see that they have this source variant, and they check they do an AND of the source type with VT byref and VT type mask, which is the basic type, like FFF. And they say, okay, if this is not the type we're expecting, basically try and do a type conversion and then go ahead and call the function. If it is the type we're expecting, just go ahead and get the value that we want. So the mask that they have there loses some information in that when they do that AND mask, they lose the VT array modifier. So if you pass in an array of objects of what they're expecting rather than just the object itself, then they will confuse an array for the basic type. So if they're expecting a COM object, like an iDispatch object, and you pass an array of iDispatch objects, it will access the safe array as if it was a dispatch object. So I actually have a demo of that, which I kind of hope is going to work. This is not very visually appealing. This is in Windows 7 with IE8, and it takes a pretty long time, but hopefully it's going to do something. It actually takes a long time, not because of crazy heap spraying or anything, but because it's trying to pull an executable down over SMB, which is time consuming. There you go. So it downloads this application and runs it. High five. So okay. Okay, the other problem that you can have with, The other problem that you can have when dealing with type confusion is direct type manipulation, and this is always really dangerous. This is basically when the developer attempts to manually modify the VT type member of the variant. And the reason that this is so dangerous is basically because whenever you're modifying the type of a variant, you're essentially desynchronizing the type from the value. And of course, the variant is unusable for the entire period of time until you've verified that it's back in synchronization with the type and value. So basically, Ryan actually found a vulnerability like this again in the ATL. And this was a bug of this nature where essentially it was in the ccom variant read from stream function. And this is ccom variant is actually a C++ wrapper class to the variant structure. So the VT value that is modified in this example code is actually the VT of a variant. And you can see that they basically set it manually. They read in a B string actually into the variant, and then if they received a type that wasn't a B string, they try and manually convert it and then set VT to reflect that. But the problem, of course, is that the change type can fail if you pass something that a B string can't be converted into, such as an array of COM objects or something like that. There's no logical conversion, so that basically fails, but VT now says it's an array of COM objects or something, and then when you go, of course this function will return an error, which later results in a call to variant clear, and that's pretty bad because it will access the B string as if it were, you know, an array of COM objects. I just wanted to talk about the NPAPI a little bit as well. So like I said before, they use the NP variant data structures rather than the Microsoft variant structures. Again, this is a language agnostic scheme, but it's a lot simpler and basically less vulnerable in many ways because they don't have the type modification and you know, kind of misleading APIs and stuff like that. So it's simpler to use and simpler to get right. But one thing that does stand out about it is the NPAPI does not actually do any type coercion. So when you use the macros that I introduced at the beginning of the talk, you know, you can do like NP variant to string to get a string out of a variant. They don't actually check anything. They just they just access the union as if it was a string. The onus is on the developer to use the NP variant is whatever type you want before you access each thing. So you're supposed to do like if NP variant is string, you know, then access it, otherwise signal an error. So of course, you know, if you've got a whole bunch of properties and methods, you have to go through and verify every single variant type before you access it. And of course, you know, you forget it once and you've got a type confusion vulnerability, which is either going to do some sort of information disclosure or result in memory corruption. So the type verification omission is basically an easy mistake to make. This is actually an example from Google's native client. It's a browser plugin that they made. I actually participated in a contest to find vulnerabilities in this product and won. And this is one of the vulnerabilities that I found where basically when you were setting properties for a couple of the objects, you can see here you've got the set property method, and if you know the property that you're going to set is a height value, you can see that they access the variant as if it's an integer, but they don't actually check if it is or not. So instead of passing in an integer for the height, you could pass in an object, and then when you retrieve that object later on, you know, there's going to be a pointer disclosure, and so you'll know where that object is allocated in memory. And these information leakage type vulnerabilities are actually becoming increasingly useful as memory protections make exploiting stuff considerably more difficult. A slightly more subtle variation on that attack, this is another example from native client actually, is that when you expose scriptable objects to the JavaScript runtime, and then you receive them later using, you know, through a parameter to a method or setting a property or something, it really you don't really know what type of JavaScript object that you've received. All you know is that it's an NP object, which is, like I said before, it's the reference count in the class structure, right? But what a lot of people do is they derive a new class off of the NP object class, and you know, this new class will have extended functionality to do whatever they want. We actually say in the paper, we've got examples in the paper that talk about this in a bit more detail, and they show example code of what it typically looks like. But if you have one of these derivative classes and you cast an object that you've received from JavaScript to this derivative class, you have no real way of knowing of whether the object you received is actually one of the derivative classes that you're casting it to. So in this particular example, native client had this unknown handle object that they'd hand out using different functions, and this function was expecting to get one of those back, but of course instead you could specify a different type of object. And so when they got the object back from JavaScript, they thought it was an unknown handle, but if you gave something else, basically there would be a type confusion for the different types of objects. And you can see they go ahead and call handle desc, which is a function out of the V table, and because you've passed in a different object, that points to, depends on the state of memory.
So the next thing we're going to talk about is trust. So the browser has evolved over time. It used to just be static HTML pages, and increasingly there's more and more content that's being included. And because of that, the security mechanisms involved with the browser have evolved over time. They've been adapted over time to meet the changing needs of these technologies. And as this has happened, the components can actually become loopholes for the altered security requirements. If a plugin was originally programmed to not necessarily support a certain protection like ASLR or DEP, it can be used to bypass those types of security mechanisms. So that graphic to the right there basically just says that we're really good at drawing images. Yeah. So, so basically what we're showing is there's a browser environment, and the browser actually authorizes a plugin. However, that plugin can rely on another plugin, and that plugin can rely on another plugin. And the problem is there's a chain of authorization where the fidelity of the authorization checks may not hold true. This functionality actually becomes very useful for subverting security mechanisms, as we found. And the trust actually becomes sort of transitive in nature. Since the browser trusts plugin A and plugin A trusts plugin B, the browser implicitly trusts plugin B.
One example where this transitive trust becomes particularly malicious is in the case of killbits. Killbits are supposed to only allow the instantiation of certain safe COM objects. However, there are a number of COM objects that are marked as safe and can be initialized without any prompting or authorization by the user, which also load other COM objects. So by simply instantiating one of those COM objects, you can then instantiate a later COM object that is not marked safe and is not supposed to be instantiated under IE. This becomes particularly bad for folks like Microsoft when they have chosen to, instead of fix a lot of the ActiveX vulnerabilities, simply killbit them. We've enumerated slightly over 100 ActiveX controls that have come out over the past, or where vulnerabilities were disclosed over about the past 5 years, where remote code execution could occur simply by instantiating the control or through a persistent stream that were not fixed and are simply killbitted. So this would allow you to through the OLE load from stream method that also exists in the ATL that allows you to read a class ID from a persistent stream, load the COM object that is mapped to that class ID, and then continue to load that object by passing the remainder of the persistent stream to that object. So when you take killbit protection plus persistence, you basically end up with nothing. So if an attacker were to provide a persistent stream with a killbitted class ID and an object embedded, they can then work off their imagination, and the end result is profit. The requirements to make this work, obviously an ActiveX control must exist that is safe for initialization. You must be able to pass the persistent stream to it. MSVid control was a perfect example of this up until lately when it itself was killbitted, but there are a number of other controls like Flash and a few others that are still able to do this. It must have a property type of VT empty, VT dispatch, or VT unknown. An important point here is that the scriptable methods through iDispatch are not necessarily accessible through this, so this is not something that where you would load up, for example, the snap view control and start calling methods and downloading executable content to a new site, to a file of your choice. You really only have access to the instantiation of the control and the persistent stream. Oftentimes that's plenty, all you need though. An interesting point to mention though is we talked about the OLE load from stream method that exists in the ATL, but as you're auditing these controls, it's also worth your while to keep an eye out for load methods that call co-create instance directly. I have it on a good word that this exists in a few places, and basically lands you in the same place.
So I get to do a demo now. Some of you have already seen this demo, but we've actually updated it, sort of a out-of-band update. So basically right here we have the kilbit visualizer. And basically this is just the debugger. And when when Internet Explorer tries to load a control, but it can't because the kilbit has been set, the program ID of the control will be logged inside of this list. However, when co-create instance gets called and the control that is being created is something that has been kilbitted, it will get logged over here. This is something that should never happen because if something is kilbitted, it should be guaranteed to never load inside of Internet Explorer. So I'm going to start that up, and I need to make sure the sound works. So we're going to go ahead and do it now. This one, the first example will show the kilbit actually working, and we'll see that happen. Hopefully. Thank you, George Michael. So now we can see that the kilbit actually effectively worked and stopped exploitation of that control. So that's good for Microsoft, but not so good for attackers. And we actually found, we'll actually show the bypass work now.
You can't always get what you want. You can't always get what you want. But if you try sometimes, you might find you get what you need.
And sort of the take-home of that is that you can't always get what you want, but to Microsoft's dismay this time around, sometimes you get what you need.
All right, we prepared a slide that we weren't sure we were going to be able to present or not. So we have to go ahead to do this. Basically, we wanted to talk about the fact that a large number of the vulnerabilities that we've talked about today were in the ATL. I don't think there's anybody in this room that doesn't know that there was an out-of-band patch that was released yesterday to address these issues, to correct the issues that existed in the ATL, to make the patches against Internet Explorer, to try to go ahead and mitigate some of the attack vectors that we've talked about today. It's an interesting problem, and Microsoft got beat up pretty bad about it in the press, and it's kind of interesting. I saw something, and this is not a direct quote, I don't remember the exact quote, but there was a line in there, something along the lines of, there's no technical reason ever why it would take 18 months to release a patch for a vulnerability like this. Well, hopefully you've seen through the entire presentation here that there may be a technical reason why it takes 18 months to coordinate a patch release for something like this, because it affects thousands of vulnerabilities across the Microsoft install base and an innumerable number of binaries that exist out there across the world. So Microsoft had the unenviable task of trying to coordinate a vendor disclosure that actually affected thousands of third-party vendors. Anyone who has compiled an ActiveX control with Visual Studio in the last 15 years may have introduced these vulnerabilities the way we described them today. So for those developers, they need to go ahead and address these issues. They need to go ahead and take a look at the advisories, the information that's been put out by Microsoft, and you're going to have to recompile your controls to make sure that you're not vulnerable to the attacks that we've documented. In addition, when you do get the new copies of the ATL, you need to make sure that you use the safe macros for defining your property maps. Do not use VT empty in the property map and perform that void star, create that void star issue that we basically talked about. And Microsoft was not unable to, but for compatibility reasons, they need to still provide the ability to load class IDs and load objects through ActiveX, but they now provide you the ability to create a list of class IDs that will and will not load. It's not just a carte blanche type thing. So when you're creating your controls and you feel that you need to be able to load another COM object from within your ActiveX control, you need to be very restrictive in that list of class IDs that you allow to be permitted in there.
Okay, so that's basically what we had. Our conclusion is essentially that these, like we said at the beginning, these interoperability layers are quite large, and it's quite an interesting attack surface. And the specific tasks that they have to perform give rise to these unique bug classes. So instead of just looking for buffer overflows and stuff like that, there's type confusion, object retention, and all that kind of thing. We presented quite a few vulnerabilities that were quite interesting in the ATL, in IE, and so on. But what we want the takeaway to be is that these vulnerability classes exist, and there's a lot more of them. We've only just scratched the surface, and I think there's going to be a lot more of them to be uncovered in the near future. So we've actually released a paper that details all the stuff we talked about today, except in considerably more depth. And there's two URLs there. There's taossa.com or hustlelabs.com. You can go and download that. And we talk about the technologies at length, and also different variations of all the attacks that we presented today that we didn't have time to do them all here. So that's basically our speech. If anyone's got any questions, we can take them now.
Ideally, if you could queue here for questions, otherwise I'll try to run around and bring you the mic. Any questions? Yes.
At what point did you realize that you had stumbled upon this deep issue that affected static ATL code?
Just repeat it.
Repeat the question. What was your reaction when you discovered what you really uncovered?
Well, so we first realized when we saw that the function name began with ATL. That was a pretty good hint, but I think our reaction was to open up a bottle of Dom Perignon.
Don't take his question.
Don't.
No.
Max Powers of the RIAA. I just want to know if you properly licensed the music you just played for this entire crowd.
George Michaels is a good friend.
Shouldn't have taken the question. Anyone else? Alvar.
So what are the odds of an ActiveX component that uses the ATL of not being vulnerable?
Sorry, can you...
What are the odds of any ActiveX component that uses the ATL not having any of the bugs that you mentioned?
It's hard to say because there's a couple of bugs in the ATL.
Well, yeah, that's zero.
It's not zero. I mean, not all ActiveX controls support persistent streams. So
Yeah, ones that don't do safe for initialization. All of them are there, right?
Yeah. The other thing is we prefer not to look at controls that don't work.
Yeah.
All right.
In how far do the patches released yesterday cover this problem? Obviously, they patched the ATL, but that's not gone into the controls. They also patched kill bits a little bit to address the issues, but that doesn't put the sign on green, I would say.
So the patch to the ATL is very comprehensive. It goes ahead and addresses all the issues that we talked about today, except for the kill bit bypass issue where I mentioned where now you simply define a list of class IDs that are loadable by the object, so that it goes a long way to restricting how that control could be used to bypass the security features. As far as the patch to IE, we haven't had a ton of time to completely validate it. Obviously, we've been working on our Black Hat talk, but I can give you one little anecdotal piece of evidence. My VM auto-updated yesterday, and it broke my demo. So I think that...
The other thing is, if you have any further questions, we can give you Mike Reevy's cell phone number.
I think also with the permissive property maps issue, Microsoft might have released a knowledge base article or something basically telling programmers how to use them, use instantiation carefully so that you don't have these these issues with the kill-bit stuff. All right.
All right. Thanks.
Thanks.